Okay, so today we're going to cover series and convergence. Okay, which is really just various tests to find out whether or not a series converges or diverges. Okay, so first we're going to try the nth term test. Well, that should be capitalized. For divergence. Okay, which states if the limit of whatever series you happen to be looking into as n approaches infinity does not equal 0 or does not exist, then the series actually diverges. Okay, now in this case, if the limit actually does equal 0, then this particular test is actually inconclusive. Actually, let me kind of block that off a little bit. And the test for divergence is inconclusive. Okay, so probably the hardest part about this section is sometimes it's easy to confuse the limit being convergent with the series being convergent. Sometimes you'll have a limit that's convergent and a series is divergent. So we're going to test various circumstances like that. Okay, so here we're actually just going to go ahead and prove this one by using proof by contraposition. So using proof by contraposition, okay, so that means we're going to show that if the series converges, then the limit is going to equal 0, which is proof by contraposition. I hate saying that word. Okay, so let's say if our nth partial sum, which we'll call our S sub n, let's say that's the first term plus the second term plus the third term, plus all the way to the n minus 1 term, all the way to some value of n, some nth term. Did I say n? Yep, I put it in there for some reason. Here we go. Partial sum. Okay. Now what if we have our nth minus 1 term, or a partial sum? Well, really, that's the same thing. You just stop at n minus 1. Which is the first term plus the second term plus the third term, all the way to some n minus 1. Okay. So just so you can see, you want to note that your a sub n is actually equal to your nth partial sum minus your nth minus 1 partial sum. Because if you subtract your a1, your a2, and everything else, everything subtracts except your a sub n. Okay, so that means if your sum from n equals 1 to infinity of a sub n actually does converge, then that means that limit of S sub n will have to equal some value of S as n approaches infinity. Uh-oh. Clean that up a little bit. And the partial sum S of n minus 1, that's really, really close to being the same thing if n gets big enough. So having that one extra term really won't make that much of a difference. So that means the limit as n approaches infinity of the nth minus 1 partial sum is also equal to some value of S. And that's just the limit value. Okay, so that means that the limit of some series as n approaches infinity is going to equal some limit of the nth term minus the nth partial sum minus nth minus 1 partial sum, since they are equal. Okay, so we've already discovered that the limit of both of those will be equal to S, which is equal to 0. All right, so this actually just proves that if it's not equal to 0, then it diverges. Okay. Strangely enough, this is not a proof that if the limit is equal to 0, then it converges. Because we have a lot of circumstances where if the limit equals 0, you'll see that it actually does diverge.
Can you move it up a little bit?
Oh, sure. Mm-hmm. Oh, let me kind of block that off since the proof is already done here. I'll do the little box like they do in the book. Okay, so there's no way to guarantee that every series where the limit as n approaches infinity equals 0 actually does converge. So it is inconclusive. When the limit as n approaches infinity actually does equal 0. And you'll see that on like multiple tests that are coming up. That even though the limit converges, or the limit may equal 0, the actual series itself would actually diverge. All right, so, anyone's still writing? Okay. All right, so let's say, for example.
Actually, could you go back for just one split second?
Oh, sure. Here we go.
Okay, thank you.
Oh, no problem. All right, so let's say, for example, if we want to determine if the sum from n equals 0 to infinity, 2 to the power of n, converge or diverge, using the test for divergence. Thing is, the hardest part about these are memorizing the conditions and the actual tests themselves. once you do, the questions can be answered in a matter of seconds. Okay, so this one, you know the limit of 2 to the power of n as n approaches infinity. Clean that up a little bit. That equals infinity, which we know is not 0. So since it's not 0, by the test for divergence, it diverges. It's a little bit close. The series actually diverges. And that's it. Okay, so let's say if we have, clean that up a little bit. Let's say for the series n equals 1 to infinity, 2n to the 6th power plus n plus 2 divided by 4n to the 5th minus n squared plus 1. Determine convergence or divergence. Okay, so if we just take the limit as n approaches infinity and divide each of the terms by n to the 5th power, you have 2n to the 6th divided by n to the 5th plus n over n to the 5th plus 2 over n to the 5th divided by 4n to the 5th over n to the 5th minus n squared over n to the 5th plus 1 over n to the 5th, which gives us the limit as n approaches infinity. That becomes 2n plus 1 over n to the 4th plus 2 over n to the 5th divided by 4 minus 1 over n to the 3rd. Clean that up a little bit more. Plus 1 over n to the 5th. Okay, so you can see as n approaches infinity, all of these will become 0. So you end up with 2n over 4, or 1/2 times n, which as n gets bigger and bigger and bigger, you just pretty much become infinity. So this equals infinity, which we know does not equal 0. So we know it diverges. Test for divergence, since the limit does not equal 0. Okay, so let's say, for example, if we have sum from n equal 1 to infinity of n over 2n plus 1. And we want to test for convergence or divergence. Okay, so that means we take the limit of n over 2n plus 1 as n approaches infinity. And if we divide each term by n, we actually end up, well, go ahead and write it out. N over n divided by 2n over n plus 1 over n. So clean that up a little bit. Which gives us the limit as n approaches infinity of 1 over 2 plus 1 over n, which that just becomes 0. So you end up with 1/2. Okay. But even though the limit converges to 1/2, the series itself, since this does not equal 0, this actually converges.
Converges?
I mean diverges, thank
Okay,
you.
that's why I was like.
That's why I said the limit converges, but this
That's why I was
diverges.
looking at you confused. I'm like, wait.
I was like, that's like too high.
And I'm like, okay, why are they looking confused? I'm like, okay, that explains why.
I was like, I knew it.
Yep, so this actually diverges since it does not equal 0. Since the limit as n approaches infinity does not equal 0, the series 1 to infinity of n over 2n plus 1, clean it up a little bit, diverges. All right, so any questions on that one? All right. So next will be our integral test. Okay, and that states if some function f is positive, continuous, and decreasing, for x is greater than or equal to 1, and some nth series, which is f of n. You can use f of x if you like. Then the sum from n equals 1 to infinity of some series a sub n, and the integral from 1 to infinity of f of x with respect to x, either both converge or both diverge. Okay, so all three of these conditions must be met for this to be true. Okay, and I'll actually have the proof in the notes that are scanned, so we're not going to really go over that now because it'll take a minute, so to kind of save on time. All right, so let's say, for example, if you wanted to apply the integral test to the series sum from n equals 1 to infinity. Uh-oh, my infinity is looking a little rough. To infinity. There we go, of n over n squared plus 1. Now, if you want, you can go ahead and just replace n with x and find your limit that way. I mean, your integral that way. Okay, so we'll just let f of x equals x over x squared plus 1. Okay, so that means if we have the integral from 1 to infinity of x over x squared plus 1 with respect to x, bless you, bless you. And a little side note where we let our u equals x squared plus 1 and our du equals 2x dx. Just have to multiply that by 2. 1 to infinity, 2x over x squared plus 1 with respect to x. Since we can't just plug in a 2 because we feel like it, just put in a 1/2. So technically we just multiplied it by 1. Okay, which is our u prime over u. So we have 1/2 times the limit as b approaches infinity, since we're using the infinite integral of natural log. You don't need the absolute value because x squared plus 1 is always going to be positive. So you can, oh, sure. Of x squared plus 1, and that's from 1 to b. Yes.
Could you just translate this to use as well? And
Oh,
you
yeah.
can say 1/2 the integral from 1 to infinity of u to the -1 du. I feel like that would be easier to.
You could.
Or not direct integration.
Yep, u to -1 du. You could have. All right, so that would give you 1/2. Uh-oh, put my limit out there. Times the limit as b approaches infinity of natural log of b squared plus 1 minus natural log of 1 plus 1, which is just natural log of 2. Okay, so if we go ahead and distribute our limit, this ends up being 1/2 times the limit of b squared plus 1 as b approaches infinity. That just becomes infinity. Keeps getting bigger and bigger. And it doesn't really matter what this is. If you have an infinity on any one of the terms, it's going to be infinity. Okay. So since the limit diverged, then the series diverges. All right. So any questions on that one? All right. I'll leave that up for a few seconds. Okay. Oh, I think anybody still writing? No, okay. Okay, so let's say, for example, apply the integral test to the series say 1/2 plus 1/5 plus 1/10 plus 1/17 plus 1/26, and it keeps on going forever and ever and ever. Okay, so your numerator is just all 1, so you don't really have to worry about that one. So if we have 1/2 plus 1/5 plus 1/10 plus 1/17 plus 1/26, and it keeps on going. For your denominator, you have 1 squared plus 1. Okay, so here you have 2 squared plus 1. For this denominator, you have 3 squared plus 1. Uh-oh. And of course, 4 squared plus 1, 5 squared plus 1, which means you end up with the sum from n equals 1 to infinity of 1 over n squared plus 1. Okay, so we'll let our f of x equals 1 over x squared plus 1. So our integral from 1 to infinity of 1 over x squared plus 1 with respect to x, actually that's our arctangent. Oh, forgot my limit since it's from 1 to infinity. So the limit as n approaches infinity, actually let me rewrite it instead of skipping steps. Oh, b. Of 1 over x squared plus 1 dx, which then becomes the limit as b approaches infinity, tangent inverse of x from 1 to b. Okay, which then becomes the limit as b approaches infinity, tangent inverse of b minus tangent inverse of 1. Okay. So as b approaches infinity, tangent inverse gets closer and closer and closer to power over 2. Especially if you consider the graph of tangent inverse. To negative power over 2. Looks like, I'm going to go this way. That. So as it gets closer and closer to infinity, this just gets closer and closer to power over 2. And tangent inverse of negative of 1 is power over 4. Which we make that 2 over 2. That's 2 pi minus pi, so that's power over 4. Which means since the limit converges, I mean not the limit, the integral converges, the limit converges. I mean the series converges. Getting mixed up. The series converges since the integral converges. All right, so any questions on that one? All right. Oh, we're at 29 minutes. Perfect timing. Should be. All right.
Did you want to start a new recording before you start the next meeting?
Yeah, I'm just going to write the title. This way the next one will start to at least the title showing. P-series and harmonic series.